Hi there, and welcome to the 9th class of the Archimedes Academy by IMSystems. It's important to understand that traction drives work different from geared drives, and that not every property can be compared by a number one-to-one. You need to see the bigger picture to really make a proper choice. And last time I explained to you how the difference affects speed, precision, and noise. And this time we're going to talk about torque and life, and also how weight plays a role in this. So, welcome to part 2 of the special characteristics of the Archimedes Drive. This class, as I said, will be about torque versus life. And we start with some terminology, because torque isn't simply torque. There are various torques in there. And again, the definitions differ across sectors and over the world, especially the annotations in here. But let's start with the most common ones. Remember a few classes back when I said if there's something heavy and you try to push it, but it doesn't move, that is because of the static friction. And then at a certain moment you push hard enough and then it moves, but there is still the kinetic friction. Well, the transition between static and kinetic friction, where it starts to move, that is the starting torque, also called the breakaway torque. But sometimes you can also drive a back in reverse, back drivability, we talked about it. And there you have a higher starting torque, and this is called the back drive torque. Now we go to the most important one, and that is the nominal torque, or also the rated torque. And that's the torque you can apply to the device while achieving the L10. And the L10 is the lifetime where 10% of the drives has failed and 90% still lives. And in the industry, it's common to set that L10 at 1 billion cycles. Although you can, for certain application, different, say, I want an L10 of 1 million cycles. This is a chart from the catalog of harmonic drive. And here you see that very well, that they have a rated torque over here, and here at 1 billion cycles, estimate the L10 end of life. However, the trajectory of a cycle is barely ever smooth, because you need to accelerate and you need to brake. And at those moments, the torque peaks a little bit. And that is what we call and there is a limit in there. And that's what we call the maximum repeated torque, or the maximum acceleration torque. And this is the max you can have every time and still achieve this lifetime. But if you would do it constantly, it would lead to a lifetime that's 1 order of magnitude less, so 100 million cycles. Next to this, there's also another one. If you look to this chart over here, you see that the fatigue strength of the flex spline in the harmonic drive will fail at a certain moment, and you always want to stay below that, because that's very soon. And if you stay below that, you have the momentary peak torque, which also is called the emergency stop torque. And what you see is that it actually also coincides with, again, an order of magnitude less, a lifetime of 10 million cycles. And what's a nice convenience, if you go 1 order of magnitude down in life, then you double the torque. So actually that repeated peak torque is twice the rated torque, and the momentary peak torque is 4 times the rated torque. So these are the values you think about when selecting your drive, in this case a harmonic drive. But you need to see it also versus the end of life, that failure mode. I already discussed with you guys that if you have at a certain moment metal fatigue and gear teeth breaks, the robot stands still, this line can't completely function, and if this whole line is standing still, then you lose millions a day if it's not repaired. But with with traction drives, you will see that the performance degrades, but it's still running, and that you can schedule your maintenance. But this is not the whole story, because not every drive will reach its end of life by just the wear and going to metal fatigue. For example, a robot can move to a wall and crash right into it with a force that's exceeding that momentary peak torque. And it's also interesting to see what the failure mode is there, because for gears, well, still it will break and you have a drive that doesn't function. But with traction drive, something different happens. Can you think about what it is? Well, I hope you said slip in your mind, because that is what happens. And does it work afterwards? Well, we'll see. In this promo video, we smash it a couple of times with a hammer. And if he starts rotating, it just does like nothing ever happens. And I have to be honest with you. We took 9 takes to make this video. And this is after it already went to trade shows all over the world for 1.5 years. So it had been abused a lot of times and it still functions. And this function we call over torque protection, because you go over that maximum torque. And you need to think completely different if over torquing doesn't mean that stuff breaks down, but just that it slips and you can continue afterwards. So I also want to add another factor, because we now talked about torque versus life. But before, in other classes, we also talked about the torque density, or the torque to weight ratio. And it's very easy to extend life by making a drive bigger and giving it more weight, because components get more sturdy. And if you increase diameters, the stresses get less. So there's a balance over there. You want to achieve that L10 that's defined while getting the maximum torque to weight ratio. And I'm going to be honest, if you compare the torque density of a Archimedes drive with its competitors, it's slightly less. It's less good if you take that classic definition of the rated torque divided by the weight. But you have to see the bigger picture, and that is that typically, if the torque increases, there's a factor called creep in our in our drives, and that relates to micro slip. And there's a linear region where everything just sticks and rolls, and a full sliding region. And in between that, you have the transition where there's so-called stick-slip behavior, and it slips and sticks, slips and sticks. And this is very important for defining our torque. So the delta 15 has been tested, and the nominal torque is at 15 Newton meters. That's the end of our linear curve. And then the full slip happens at 90 Newton meters. So that's completely different, because over here, you don't only pick your drive because of a rated torque. You also think about what's the maximum torque it will endure, and is that lower than the momentary peak torque. But for us, that's something you don't care about. We don't care if you go at twice the nominal torque or 20 times the nominal torque. It'll just slip and function as it should afterwards. So yes, torque to weight ratio of an Archimedes drive is slightly less. But if your application needs to go to big peak torques, then maybe the Archimedes drive is better despite that slightly worse torque to weight ratio. So I hope I gave you a clear picture to make a fair assessment of the torque capacity you really need, and if the failure mode has an impact on that. Thank you for watching, and see you next time.